In the mid-20th century, mathematician John von Neumann formalized a design that would become the physical blueprint for almost every computer on Earth. The core of the von Neumann architecture is strict physical separation. The central processing unit and the memory are distinct components. To run a program, a system must pull a single packet of data from memory, process it in the CPU, and push it to an output device, executing instructions in a strict sequential line. This step-by-step model was highly reliable. By continuously scaling the speed of this sequential processing, early mainframes successfully executed massive mathematical calculations and managed global commercial databases throughout the 20th century. But processing instructions one at a time creates a structural bottleneck. While a sequential system is perfect for rigid arithmetic, it fails when forced to process the continuous, overlapping, and highly ambiguous data of a live physical environment. To build systems capable of solving complex, autonomous problems, like navigating a city or interpreting human behavior, the physical and logical constraints of the von Neumann bottleneck have to be abandoned. Early automation relied on heavy, pre-programmed robotics operating in highly controlled factories. They executed static, repetitive tasks where the environment never changed. Modern computation demands systems that navigate unstructured spaces. A program must now recognize individual faces in a crowd, optimize chaotic traffic routes in real time, and anticipate human needs before a command is ever typed. This requirement has pushed computer science into intelligent and emotional computing, often referred to as conseil. Here, machines are tasked with interpreting non-binary human emotional states, like frustration or satisfaction, and adjusting their response accordingly. Achieving this level of physical and emotional intelligence requires a reconstruction of the relationship between software algorithms and the physical hardware that runs them. To understand where computation is heading, we have to first deconstruct the distinct software models currently grouped together under the label of artificial intelligence, and then examine the physical components required to run them. Artificial intelligence is not a single monolithic program. It is a collection of specialized algorithmic frameworks, heavily inspired by systems already functioning in biology. This diagram outlines the neural network framework. Modeled after the nervous system, it solves pattern recognition problems. Data enters the input layer, filtering through hidden nodes in the center. Adjusting the weight of these connections lets the network identify patterns, like a fingerprint. When a problem requires optimizing an unstructured environment rather than just identifying a pattern, developers shift to a second major framework, known as a genetic algorithm. By utilizing the biological principle of natural selection, a genetic algorithm generates thousands of potential iterations at once. It tests them, discards the failures, and evolves the surviving code until it finds the most efficient solution, like calculating the fastest physical route on Google Maps. Looking at the bottom diagram, we see the third framework, the expert system, designed to capture the knowledge of a human specialist. It maintains strict separation of duties. An inference engine processes operational logic, drawing data exclusively from an isolated, curated knowledge base. Yet, despite their complexity, neural networks, genetic algorithms, and expert systems share a common limitation. They are entirely reactive. They sit idle in a server until a human user inputs a query or prompt. True machine independence requires taking these static analytical models and embedding them into continuous, self-directing entities. This brings us to the software agent. It shifts how software interacts with its environment, operating autonomously and continuously without waiting for human input. This diagram maps the architectural loop, making continuous independence possible.
The agent uses sensors to read percepts from the environment. It processes this data, makes a decision, and uses effectors to take action, altering the environment and restarting the loop. Unlike a reactive program waiting for a command, an agent is proactive. It has a designated goal, and it actively learns and adapts its behavior to achieve that goal over time. When thousands of these individual software agents are deployed into the exact same environment, it forms a multi-agent system. Multi-agent systems are deployed to solve massive, dynamic problems that a single program cannot handle. They balance real-time energy loads across smart power grids and execute high-frequency financial modeling by evaluating thousands of competing variables simultaneously. Running thousands of independent learning agents at the exact same time requires a volume of parallel data processing that exceeds the sequential speed limits of classical von Neumann hardware. Software has outpaced hardware. To process these dense, multi-agent environments instantaneously, physical machines must transition away from step-by-step sequential execution and embrace massive simultaneous processing. While current graphics processors allow for high degrees of parallelization, the extreme data volume of ubiquitous environments is driving the development of quantum computing. This hardware uses the mechanical phenomena of quantum physics to solve problems that are mathematically impossible for classical silicon transistors. This graphic illustrates the foundational difference. On the left, the classical bit is strictly binary, existing entirely as a 1 or 0. On the right, the quantum qubit utilizes superposition, existing as a complex probability of both 1 and 0 at the exact same time. Superposition removes the sequential bottleneck completely. Instead of testing one potential outcome after another in a straight line, a quantum processor can evaluate millions of possible solutions instantaneously. These extreme processing speeds are actively being directed toward computationally heavy tasks, like advanced cryptography, filtering unstructured big data sets, and complex chemical mapping for drugs. Today, quantum computers are massive, delicate machines, isolated in super-cooled laboratories. But their true purpose is to serve as the invisible, centralized brain powering millions of distributed edge devices. We are now seeing the convergence of these technologies, massive, centralized quantum and AI processing power connecting to tiny, localized sensors embedded throughout the physical world. This network creates a theoretical model known as ubiquitous or pervasive computing, an idea initially proposed by computer scientist Mark Weiser. The core philosophy of ubiquitous computing is that processing power is no longer confined to a glowing screen on a desk. Instead, it is invisibly woven into the fabric of everyday objects and environments. Here, the software agent loop is deployed at scale. Mundane objects, thermostats, lighting fixtures, and mobile phones now act as the active sensors and effectors continuously communicating with the broader environment. We already rely on primitive versions of this. An anti-lock braking system in a car utilizes machine-to-machine consistency, operating autonomously to pulse the brakes and save lives without waiting for a human driver's input. In a truly ubiquitous environment, human interaction with computers evolves from active to passive. We stop typing commands into keyboards and instead naturally supply data through our physical presence and continuous health monitors. The staggering volume of data generated by an entire smart city relies entirely on the parallel processing structures of AI and the physical limitations broken by quantum and biologically inspired hardware. The trajectory of information technology leads away from the sequential calculator and toward an invisible, emotionally intelligent, and biologically inspired computational web.